Okay, so, well, a little bit delayed, but very happy to get started with the first lecture here. And so, it has the usual title, right? So, okay, yeah. So I think I've heard versions of this talk 2 or 3 times, and I read the paper 2 or 3 times, and I actually really learned a lot from it. I think it's also a really great way to start a summer school on quantum gravity, and it is touching getting into some of the, at least the paper gets into some of the cosmological questions as well. So I think this is a really nice sort of background. I mean, there's really interesting issues here. I think it also should be really interesting kind of background for a lot of things we're going to be thinking about. So I'll shut up now, and David, please tell us about quantum gravity at low energies.
Thank you. Can everyone hear me okay? Great. I'll just reinforce the comment. As far as I'm concerned, absolutely please interrupt anytime you like. I'm not even bothered about whether it's clarification or not. I'm happy to shut something down if it ends up being radically derailing, but otherwise by all means try it. And absolutely, if there's something I'm saying that doesn't make sense or you're confused by it, then ask about it, because it's bound to be widely shared. Okay, so this is kind of partly a lecture about what we mean by quantum gravity and about the fact that there's a kind of tacit ambiguity in what it means in the physics literature that hasn't always been recognized in the philosophy literature or even sometimes in corners of the physics literature. And the starting point maybe is this line on what quantum gravity is, which you'll see very widely in philosophical discussions of quantum gravity. So common definitions of quantum gravity you'll see. I shan't source these, but there's some source versions in the background reading paper that the talk's based on. You often see it claimed that quantum gravity is any theory, any physical theory that combines general relativity and quantum theory. Or if you want to be a bit more careful about that, it's supposed to be any physical theory that's got some kind of limiting case or special regime that looks like quantum theory, and some other limiting case or special regime that looks like general relativity. Okay. As far as that's a definition, of course, you can't really quibble with the definition. Here are some claims that are made about quantum gravity under that definition. So the most noticeable one you see being claimed is we don't have a theory of that kind. Or more specifically, we don't have a theory of quantum gravity in the same way that we have an acceptable quantum theory of the other interactions in nature. So if you're sufficiently concerned about various sorts of mathematical rigor, or if certain foundational problems in quantum field theory exercise you enough, you might want to say, well, we don't have a perfectly satisfactory theory of any of the other interactions. If you're particularly worried about, say, how to think about quark confinement, you might want to say we don't have a completely satisfactory theory of the strong interaction. But there's clearly some substantial sense in which we have a good, successful, working, testable, tested theory of the other interactions in nature at the quantum level. And the claim is we don't have a quantum gravity theory in that sense. That's claim one. Claim two is we don't actually need one empirically. More specifically, yes, there are super esoteric regimes in which we would need a quantum theory of gravity. So maybe we need a quantum theory of gravity in the very, very, very early universe at Planckian curvatures before even inflation kicks in. Maybe that's a regime where quantum gravity would matter. Maybe if you fall into a black hole, then the last nanosecond of your survival will rely on quantum gravity or more actually, the last nanosecond of the manner of your gruesome demise will require quantum gravity to study it properly. Maybe even outside the black hole, maybe in very long time environments when you're studying the evaporation of black holes by Hawking radiation, as you're considering questions of information loss, I'll talk about a lot on Wednesday. Maybe again, that's a situation in which you want quantum gravity, but only esoteric situations of that kind. Really extreme cases that we have no observational or empirical data on and have no prospect of observational or empirical data. And so that makes it, in some corners of the philosophy literature here, a wide open question to ask as to even why you should need a quantum theory of gravity. If there are no empirical phenomena it really speaks to, why do we care? And then it can come down to a sort of conceptual hygiene or a preference for unification or things of this kind. Okay, so the main take-home, if you like, the minimal take-home part of the talk, or the first part of it, is those claims aren't true. at least on the way I defined quantum gravity at the beginning of the talk, these claims are not true of quantum gravity defined that way. Or to turn it around, insofar as these claims are true of quantum gravity under some definition, then that definition isn't anything like as simple as just quantum theory, anything that combines quantum theory and general relativity counts as a quantum theory of gravity. Holding on to the idea that the definition of quantum gravity is the one I gave at the beginning, any theory that has classical general relativity and quantum mechanics as some kind of limiting cases, here are some more positive claims about quantum gravity that I want to kind of discuss and explain in the rest of the lecture. So claim, we do have an acceptable quantum theory of gravity in almost exactly the sense we have an acceptable quantum theory of the strong or weaker electromagnetic interactions. And more specifically, that theory is just the quantum field theory that we get if we take general relativity and apply modern quantum field theoretic methods to it. Now, that theory, to be mathematically well defined, can't be true at all length scales. More specifically, if you try using those methods to define the theory and then try to study the theory at scales close to the Planck-scale, the particle collision energies around the Planck energy, for resolving length scales around the Planck-scale, then the theory will break down. So the only way to understand the theory in this sense requires you to understand the theory as cut off at some high energy threshold, at which point it gets replaced by some new and genuinely unknown theory. But guess what? That's true for our best quantum theories of the non-gravitational interactions as well. Our modern take on quantum field theory is that quantum field theories are effective theories. They're not supposed to be the last word. They're not supposed to be true of the world without qualification. They're supposed to describe the world at certain scales in certain regimes and fail at energies higher than those scales. And thus understood, quantum gravity has a ton of evidence behind it. A very large amount of observational data supports that theory, or more accurately and more carefully, supports certain aspects of that theory. Now, I don't want to oversell this. It's certainly true that this low-energy theory of quantum gravity has a bunch of interesting conceptual, mathematical puzzles, concerns, issues to raise. That's good news for people working in the boundary between physics and philosophy. I think there's a ton of questions to ask about that theory that can be pushed and explored. But it's important to understand what you're asking those questions about is a theory that's at least under tolerable mathematical control, that's under enough control we can calculate in it, and which actually is richly responsive to observational data. Okay, let me start making a case for that. So this is an audience participation. Some of you may have heard this argument before. Find some object on the table around you. Probably your notebook's a good example. It needs to be it needs to be heavier than air, and it also needs to survive moderate impacts. Your keys will also do. Your water bottle, yeah, that'd be fine. Okay, right, pick it up, lift it a little bit above the table. Okay, let go. Congratulations, you just tested quantum gravity. We were talking yesterday at the dinner about how these days big physics has got so expensive that it costs you billions of dollars to do foundational experiments. That's not always true. So if you think about the experiment, what you did is you took the object, you let go of it, it accelerated downwards under gravity, or if you like, it remained in free fall while the room accelerated upwards, if you're in love with general relativity and the equivalence principle, accelerated downwards under gravity, then it stopped abruptly, didn't continue on free fall through the Earth. Our understanding of its downwards trajectory requires gravity, and our understanding of the fact it stopped requires quantum mechanics. So if quantum gravity is any theory that combines general relativity and quantum mechanics, you need a quantum theory of gravity to study what just happened there on the table. Now, perhaps I'm too quick to say that requires general relativity. It was a non-relativistic description we just had. So it's definitely true that you need a higher budget to test the combination of general relativity and quantum mechanics. you need a significantly more expensive piece of kit. Specifically, you need one of these, or a smartphone. If you open up your phone and you check your sat-nav and you confirm that you're in this room according to Google Maps, that's a quantum general relativity prediction. You can't understand the workings of the electronics in your phone without quantum theory. And it's famously the case that the GPS satellite network requires general relativistic understandings of gravity and not just Newtonian gravity to make sense of it. If you want something slightly more genuinely expensive than that, the atomic clocks that have been used to test relativistic time dilation and their sort of photonic clock successors are also phenomena that need both quantum mechanics and gravity to understand. You know, famously, back in the day, people put atomic clocks in aircraft and flew them around the Earth and brought them back, and thus measured the subtle level of time dilation that you get from the combination of general and special relativity. These days, the clocks are a bit more sensitive. You can sort of just push them up a few inches or a few millimeters and observe that the clock slows down just as a consequence of being higher up. Those clocks, of course, are richly quantum mechanical systems. We don't have classical theories of how those clocks work, and yet we're testing a quantum mechanical phenomenon. So the physics of the atomic and photonic clock tests of GR is also quantum gravity physics in the way we've described it. Now, that might be thought to be cheating in some ways. Here's one reasonable instinct one can have as to why it's cheating. This is gravitation, but it's not self-gravitation. So you might think, well, there's a division of labour. Maybe the way it works is we ask classical general relativity to tell us the gravitational field, or equivalently tell us the local metric, and then we do quantum field theory or quantum mechanics on that background metric. And occasionally, even in statements of what quantum gravity is, you see that qualifier. You see people saying, well, we have in mind quantum self-gravity. Mere quantum field theory on curved space-time isn't what we have in mind. But there are many, many situations in which we need both quantum mechanics and self-gravitation. Summary of what we had. Here's an example. Just think about the Earth. If you want to understand the structure of the Earth, well, the Earth's solid, citation needed, but fairly solid. Solid matter, our understanding of solid matter is quantum mechanical, but the Earth is self-gravitating. Understanding the structure of the Earth, solving the equations of state for the Earth, is about taking an equation of state for matter that requires a quantum mechanical understanding and solving it against the background of its own gravitational field in a self-consistent way. It's probably, there's room to worry, I suppose, about whether we really should call our understanding of the equations of state of the Earth quantum mechanical rather than phenomenological. I mean, I haven't, to be honest, checked, but I seriously doubt that geologists solve the Schrödinger equation very often. I don't know how good our understanding of the equations of state used in geology are in terms of quantum mechanics. So we can go to a situation that's less ambiguous from that point of view. Think about the sun. I mean, the sun is well treated as a dilute gas, or in its core, a dilute plasma. Let's stipulate that classical mechanics adequately describes the statistical structure of fluids like that. I think there's room to query that, actually, but that's a whole other talk. But let's stipulate that we can understand the equations of state of the fluids of the sun in classical terms. But the energy source in the centre of the sun is nuclear fusion, which we need a quantum mechanical description of. And the percolation of light from the core of the sun out to its atmosphere and beyond likewise is quantum mechanical. We need a quantum treatment of the scattering and re-radiation of light in order to understand stellar opacity, to understand heat transport inside the sun. So solving the sun is a quantum gravitational problem. I need simultaneously to consider the self-gravitation of the matter of the sun and the quantum mechanical nature of the matter of the sun. If you look at stars a bit smaller than the sun, you'll even need quantum mechanics to handle the equation of state. If the sun was maybe half as big as it is, then its core becomes degenerate. It starts being held up not just by classical pressure, but by the pressure of the Pauli exclusion principle, the requirement that the denser together I put electrons, the wider they need to range from momentum space. Likewise, if you look at white dwarf stars, the corpses of stars like the Sun, here's Sirius B. White dwarf stars are balls of degenerate matter. They're self-gravitating balls of degenerate matter. Understanding what their structure is quantum gravity, under our definition of what quantum gravity is. Now, this is all Newtonian again. So I've thought about planets, I've looked at stars, I've looked at white dwarf stars. It doesn't take too much effort to come up with fully relativistic or general relativistic cases where we need a quantum gravity description. So here's the Crab Nebula. The Crab Nebula is a remnant of a supernova. Supernovas are paradigmatically quantum gravitational in our definition. We need a full relativistic treatment of gravity. Supernovas are far too excitable for Newtonian approximation to do it. We need a full relativistic quantum mechanical description of the physics of the supernova. There's a lovely observation that I quote in more detail in the paper of this, that supernovas might be the only place in the universe where it really matters that neutrinos obey the Pauli exclusion principle. Also look at cosmology. In the current epoch in the universe, the contribution to the cosmological dynamics of the radiation in the universe isn't very large compared to matter in the universe. Go earlier in time, that stops being true. So if you take the universe and you let it expand, then the energy density of the matter in the universe goes down as the cube of the effective size of the universe, just because it's spreading out. The energy density you're getting from radiation goes down as the fourth power of the size of the universe, because not only is it spreading out, it's redshifting. So as the universe gets older, the matter contribution is more and more important, and the radiation contribution is less and less important. In the early universe, very early universe, the radiation component is playing a substantial role. What is that radiation? It's black body radiation. It has this equation of state. Its energy density is proportional to the fourth power of its temperature. That's a quantum mechanical calculation. Famously, if you try to do statistical mechanics on classical electromagnetism, you reach paradox and infinity. This is the ultraviolet catastrophe that led Planck to the light quantum and got this whole game started. So if you want to understand cosmology, you need a quantum mechanical description of the radiation field coupled to full general relativity. So, claim. We have a bunch of situations in which we have quantum mechanical matter plus general relativistic self-gravity. And I've kind of laboured this just to make the point, really. I mean, a huge fraction of our astrophysics is quantum gravity, in the sense that a huge fraction of our astrophysics requires us simultaneously to be considering the self-gravitating features of matter and the quantum mechanical features of matter. You'll often see it claimed that there's a kind of separation of magisteria in quantum gravity, where there are phenomena in the world that need classical general relativity to describe, there are phenomena in the world that need quantum mechanics to describe, and there's basically nothing in the middle. That's just flat false. And you just need to look at astrophysics a bit to see that it's false. Okay, so if we're using quantum gravity in this context, then we ought to be able to say, well, what are the assumptions about quantum gravity we're using in doing astrophysics? They're usually pretty tacit, but with a little bit of care, you can tease them out. And I think effectively what we're using in most of the astrophysics examples I've been discussing so far is what people in quantum gravity research call semi-classical gravity. So here I've got the Einstein field equation. On the left-hand side, I've got the usual Einstein tensor plus a cosmological constant. On the right-hand side, where classically I should have the stress-energy tensor of the matter, I've got the quantum mechanical expected value of the stress-energy tensor. And I'm also putting quantum field theory, or almost always some appropriate approximation or tractable regime of quantum field theory, on as my description of matter. And furthermore, I'm only using this in the situations where the fluctuations are very low. So if I work out the equation of state for a quantum fluid, I work out the expected value of the stress energy tensor, and I also check that the fluctuations in the value of the stress energy tensor are very small compared to the value of the stress energy tensor. So claim the assumptions that we're making in these astrophysical applications of quantum gravity are basically assumptions of this form. We're working out the expected value of the stress energy tensor quantum mechanically. We're getting an equation of state, which we sort of rely on as describing not just expectation values, but actual goings-on under the assumption fluctuations are small. We couple that to GR, and we solve self-consistent. In fact, I go a little bit further than that. It's not just, I think, that a lot of applications of gravity in astrophysics have this form. It's that actually this version of general relativity, this semi-classical version, is much more observationally well tested than what you might call classical general relativity. And let me spell that out a bit more. So here's the sort of abstract form of what we mean by a model of general relativity. In the language beloved of philosophers of spacetime, I have a triple, M a manifold, G a metric on that manifold, phi some matter stuff, placeholder. Whatever the matter is, phi is representing it. I have some dynamics for phi. I have the Einstein field equation that couples a functional of the metric alone to some functional of the metric and the matter fields. And then I have an expression for what that actual functional is. I have an equation of state, if you like, for what the stress energy tensor object is that acts as the source of the gravitational field. And I claim that's just the general framework by which we apply general relativity. So then you can subdivide applications of general relativity according to how the matter field and the stress energy tensor bits are filled in. And I think you can helpfully recognize sort of four regimes of that. The first of them is vacuum general relativity. I represent the matter field very straightforwardly. I deny their existence. Or more reasonably, I say, in the regime I'm dealing with, they can be neglected. Second regime, phenomenological general relativity. I say, I have no interest in a microphysical description of the matter, or maybe I have an interest, but too bad, I still haven't got an understanding. I'll treat the matter as something like a fluid, or a dust, or maybe compact planets, or something like that. Third case, what theorists would call classical general relativity. So now I have GR, and I have some classical fields. Maybe I've got the electromagnetic field, maybe I've got a Klein-Gordon field, maybe I've got a Dirac field. My theory is a coupled dynamics of those classical matter fields and the classical metric, and my dynamics is given by some action, and my stress energy tensor is expressed as the variational derivative of the matter action with respect to the metric. You know, insofar as we talk about GR as a classical yet microphysical theory, I think this is normally what we mean. We distinguish it from the phenomenological theories, which don't even pretend to be theories that give a microscopic fundamental analysis of the matter. And then finally, we have semi-classical GR in the form I've just been discussing. The matter is a quantum field. The stress energy tensor is the expected value of some stress energy tensor defined by the action that's used to define the quantum field. Okay, so then we can ask for these applications, for these sets of models, what applications do we have? What tests do we have of these theories? So we have quite a few applications of vacuum general relativity. Gravity waves of vacuum general relativity. Black holes, pretty soon, of vacuum general relativity. I mean, debatably not if I've got an accretion disk or something, but let's say the kind of the collisions of black holes in the pitch dark, as Jana Levin puts it, that LIGO looks at, are vacuum general relativity situations. Vacuum general relativity has a ton of evidence in favour. We have a lot of applications of phenomenological general relativity. Anytime we apply general relativity in the solar system, we're not typically having some microstructural equation of state for the planets. We're just treating them as points or as test particles or something. If I'm doing the gravitational field of the sun in general relativity, I don't do a microanalysis of it. I just say, okay, fine, it's spherically symmetric. Let's use the Schwarzschild solution and call it a day. And other bits of astrophysics and cosmology have this character. You know, if cosmology often will simply assume a sort of fluid model. You know, the fluid is a fluid of galaxies. Let's say we're abstract. We're ignoring fluctuations on scales less than 100 megaparsecs or something. So again, phenomenological GR has lots of evidence behind it. I spent the first part of the lecture making the case that semi-classical general relativity has a lot of applications and a lot of evidence behind it. In fact, I think the boundary between semi-classical general relativity and phenomenological general relativity is kind of blurry. I mean, it's almost never the case in physics that we have a completely mathematically rigorous derivation of some high-level description from a microphysical starting point. We normally have an argument that has a bunch of sort of lacuna and steps and approximations controlled to various degrees. And I think there's a kind of borderland you get to as your approximations get less controlled and your arguments get more hand-waving, where you come out of the borderlands and now you're doing phenomenological general relativity, and you come out of the borderlands in the other direction and you're doing semi-classical general relativity, and somewhere in the borderlands you can't quite say what you're doing. But I think in the regime of gravity plus matter, and specifically in the astrophysical regime of gravity plus matter, between them, the phenomenological and the semi-classical aspects of general relativity lick the platter clean. They more or less cover the basis. Okay, so let's talk about applications of classical general relativity. Well, let me know if you find any. Unless you count vacuum general relativity as a special case, but of course it's a special case of all of these. I don't know of any situation where the admittedly beautiful theory of classical gravity coupled with classical matter fields under an action principle has direct empirical applications. And that's kind of not very surprising, because the world is not replete with classical fields. It's got gravity, but that was the vacuum bit already. It's got electromagnetism, and you could theoretically imagine situations in which classical electromagnetism plus gravity was describing something empirically relevant. But so far as I can see, that's never the situation we actually find ourselves in, where we have electromagnetism plus gravity. We have lots of empirically relevant situations where we have black body radiation plus gravity. But as we've just seen, black body radiation is quantum mechanics to understand it. I can theoretically imagine maybe that the magnetic field of some neutron star might be so extraordinarily strong as to give rise to, in principle, detectable violations or deviations from vacuum GR inside the magnetic field. I haven't done a calculation to check that, but it doesn't strike me as wildly implausible. But neutron stars are not vacuum situations anyway. To understand the neutron star situation, I need tons of quantum physics to understand the sort of the fluid of neutrons that makes the star. So as far as I can see, yeah, go ahead.
Do you consider the background evolution during inflation or dark energy model by scalar field as an example of this?
So do you want to call that classical?
I mean, if I don't quantize the field, because I just want to see, I have a classical quantization for the field, and I just see the field rolling down and model dark energy or model inflation.
So, look, it's a nice example. What I want to know is, okay, do we have an understanding of that separates away from our quantum mechanical understanding of the setup? So, and I don't know enough about this. It would be a nice thing to look into. The way I understand it, I'll come back to inflation in a minute. Actually, the way I understand and think of inflation is it's a QFT setup. It's I've got a quantum field. I need to look at the quantum fluctuations in it to get my source. But you might want to say, okay, I want to go a bit downstream from that. I've got my fluctuations, never mind how. Can I study that little bit of the regime purely classical? It's a nice example, maybe. Yeah, maybe. I mean, if so, I think it's a fairly pyrrhic victory if so, because I think what you're seeing is a little regime of something whose broader description is quantum mechanical, nonetheless has a good classical approximation. But it's a good point. Yeah. Yeah, good bonus.
That's like inflation, I think might be a harder case, but for people who model dark energy like quintessential fields, I don't think they worry about quantizing the field and multi-fluctuations necessarily. It's just like background evolution.
Yeah. Good. Okay, but then the problem there is that's not something that we've confirmed observationally. I mean, yes. So it's perfectly possible. There could be. We don't know everything, and there are deep mysteries in cosmology, and it's entirely possible some of those mysteries might end up being something that's usefully discussed as a classical field plus GR. I mean, I don't know that example super well. An example I know slightly better, there are field models of dark matter. So if actually there's a dark matter field or something, then it's not true that there are only two long-range classical fields, and there'd be a third that might be showing up. So it's not, so I don't want to suggest there's something conceptually impossible about an application of classical GR. And indeed, you know, if you had a sufficiently large budget, you could just generate an incredibly strong classical coherent magnetic field or coherent laser beam or something and measure its gravitational effects. What I want to claim is that's not the regime we actually have evidential confirmation. Whereas the thing we have got the evidential confirmation for is the semi-classical version where I've got the more quantum mechanical description. But yeah, I think those are nice points. Thank you. Okay, but I don't want to tell you that semi-classical gravity is low-energy quantum gravity. I said at the beginning that we have a perfectly satisfactory quantum theory of gravity at low energies. Semi-classical gravity isn't it. For all of its remarkable application, it's limited in its application, or at least has been limited thus far in its application, to situations in which the quantum fluctuations in the stress energy are really small, or really small compared to their absolute values. And that's, by the way, really, really standard in physics. So these kind of semi-classical methods come up all over the place in physics. An example that you've probably studied, or at least looked at without noticing you're studying it, is the way we describe electron shells in atomic physics. So if you think about some atom with a bunch of electrons around it, the normal way you describe that in sort of atomic physics, atomic chemistry, is you say, well, there's a bunch of energy levels, and the electrons fill up the energy levels. So the first two electrons sit in the S shell, and the subsequent electrons sit in the subsequent shells, and you make your way out. And if you've got a big complicated atom, then your shell structure gets super complicated, and I'll start to forget what it is and embarrass myself. But anyway, there's a shell structure. But if you think about that, you can see that can't be pure quantum mechanics, because if I've got n electrons, then the joint wave function for those n electrons doesn't live in free space. It lives in 3 n-dimensional space. And I can have all manner of entanglement. So what I'm actually doing in studying the structure of atoms is using what gets called the Hartree-Fock approximation, which is a certain approximation regime in which I say, well, the correlations between electrons, or the entanglement between electrons, can be appropriately neglected relative to the overall electron effect. So I'm saying the fluctuations are small enough that I can get away with treating the movement of each electron as happening in the collective electric fields of all of the electrons. But of course, you'd expect that kind of method in electromagnetism to break down in the case of fluctuations. If I have a big chunk of electric charge, and I place that electric charge in a superposition of being here and being here, and I bring in a test particle, then the semi-classical description would say you'd expect the test particle to accelerate towards the expected value of the charge. In other words, you'd expect the test particle to thread the needle between the two places in the superposition. But that's not actually what you'd expect in quantum theory, and it's not what we find. What you actually find is that the electron gets entangled with the charge distribution. So I actually get a superposition of charge here, electron going here, or plus charge here, electron going here. If you're one of these strange people who finds the Everett way of talking about quantum mechanics helpful, then you can say, I've actually got a branching situation here. In one Everett branch, the charge is here and the electron goes this way. In the other Everett branch, the charge is here and the electron goes this way. So you have a breakdown of semi-classical electrodynamics in the case of large correlations, large fluctuations. So we generally expect the same in the gravitational case. In fact, we can test that. In fact, we have tested that. There is a slightly tongue-in-cheek experiment done by Page and Gailka back about 40 years ago, where they say, okay, fine. I will take a large mass and I will place it in a quantum mechanical superposition of here and here by the rather straightforward expedient of measuring, I'm not sure what they actually did, but in effect measuring a spin-half particle, and if I get spin up, putting it here, and if I get spin down, putting it here. And then I'll take another rock, a smaller test particle, I'll measure the gravitational force, and I'll see whether what I find is that the gravitational force points towards the left position, points towards the actual position, i.e. to the left 50% of the time, to the right 50% of the time, or whether it points to the space between the two places where the mass are. They actually did the experiment. You may or may not be surprised to hear that the result falsifies semi-classical gravity. The distribution gets pulled to where the mass actually is. I asked Don Page about this a couple of years ago. I happened to meet him at a workshop. And I asked him whether they actually seriously expected to get any other results. And what he said was that, thinking about sort of the chaotic and random processes in the early solar system, you kind of expect that the quantum state of the solar system has a superposition of the Earth in lots of different places, so that we'd feel the gravitational force of the Earth not towards the centre of the Earth. So the fact that we actually experience the gravitational force of the Earth towards the centre of the Earth seems to be pretty good evidence that semi-classical gravity was false. But it was nice to check, he said. Okay, but that does have a slightly foundational feeling about it. I want to defend the claim the Page-Gallagher experiment is substantive and genuinely does count as falsifying semi-classical gravity. If we have time in the questions, maybe we can talk about how interpretation dependent it is. I want to claim it doesn't depend on the Everett interpretation. It holds in the vast majority of approaches to quantum mechanics that count as interpretations of quantum mechanics rather than self-confessed modifications of quantum mechanics. It wouldn't hold if you had a genuine dynamical collapse where wave function collapse really happened as a physical process. But outside that regime, I want to claim it's pretty genuine. But it's got a kind of foundational feeling to it. It's a bit, there's this disreputable feeling. It's a bit like the measurement problem. Here's a much more, this goes back to the question earlier. Here's a much more direct example in reputable physics, if you like, of where we need quantum gravity, but outside the semi-classical gravity regime. So I'm sure everyone recognizes the cosmic microwave background radiation. It's inhomogeneous, it has fluctuation structure. Our best working understanding of the fluctuation structure is these are inflations spread out and early universe physics mediated results of the fluctuation structure in some inflaton field in the very, very early universe. If you try to model that in semi-classical gravity, and I'm talking here about modelling at the point at which we're doing the quantum fluctuations, not the downstream period we were talking about earlier. If you try modelling that in semi-classical gravity, you won't get fluctuations in the matter distribution. And the reason for that, of course, is that if I've got a quantum field and the expected value of the field is uniform, the fact that it has fluctuation structure doesn't change the fact that the expected value remains perfectly uniform. So if matter responds to the expected value of the inflaton field, or the gravitational field is determined by the expected value of the inflaton field, then those fluctuations are inert. They're not doing anything that gives you the anisotropies that we need to understand structure formation. So whatever it is that we're doing in these kind of inflation stories about structure formation, we're not doing semi-classical gravity. We can't be doing semi-classical gravity. But of course we don't need to theorize a priori as philosophers as to what is being done in these calculations. We can just go and read the calculations and see how they work. The one I use for the discussion here is just Weinberg's textbook discussion of it in his Cosmology textbook. There's a vastly more complicated versions of this, many of which are above my pay grade, but that works as a nice elementary structure. What we're doing there, what Weinberg does, the LEQG generally does, is something somewhat different from the semi-classical physics. I take my metric, I split my metric into a fixed part and a fluctuating part, and I treat my fluctuating part as a quantum field defined on the background of my fixed part. So for these inflation cases, typically I'll take my fixed part as just being the homogeneous isotropic expanding universe, and the fluctuations around that, the actual metric minus that homogeneous isotropic bit, that I'll shove a hat on and call it a quantum field and use QFT methods on it. That works in the sense that let me say a bit more about it. It works in the sense that you can do calculations in it. You can do calculations in the regime, this is what Weinberg does, I do calculations in the regime where the gravitational degrees of freedom are frozen out, and the metric fluctuations are just slaved to the matter fluctuations. But I can also do it in regimes where quantum fluctuations in quantum mechanical degrees of freedom of gravity matter, where I've got a graviton gas interacting with the matter fluctuations. If I do that, I can get inflationary predictions, and of course those are observationally testable. Now, it's obviously true to say that the evidence base we have from the CMB fluctuation structure for particular models of inflation is a great deal thinner than our evidence for semi-classical gravity in the astrophysical context I'm describing earlier. I actually think it would be a terrific HBS project to look more in detail at how the sort of pipeline goes from the theoretical models to the kind of discussion of the various peaks in the CMB multipole spectrum, and try to understand how, which bits of this complicated theory are being exposed to the evidence and which bits are only rather loosely attached. I don't know the answer to that question. I'd love to know the answer to that question. But it's obviously going to be the case that early universe cosmology data constrains quantum gravity much less tightly than astrophysics constrains its semi-classical applications. But it constrains it. It's awkward to get data from that regime, but it's way easier than making measurements inside the event horizon of a black hole or in some pre-inflationary Planck level of curvature. These are somewhat extreme situations, but they're still low energy situations. They are, to some degree, accessible observations. Okay, but this theory is also not very satisfactory, conceptually. It's long recognized in the quantum gravity literature. It's not very satisfactory. Here are some problems with it. Firstly, how in a principled way do you divide the metric field into fluctuating part and background part? Secondly, doesn't the very idea of making a division of that kind in your very definition of the quantum field theory get in the way of one of the things that we're told to love and cherish about general relativity, which is it's background independent? It's not supposed to describe goings-on against a fixed canvas. It's supposed to give us a dynamical canvas. And also, what's the connection between this way of describing things and the semi-classical way that I spent a while earlier trying to argue was the core of most of our applications of quantum gravity? And what I want to say in the next bit of the talk is that apparent disconnect and those apparent problems are not real problems. They're understandable by having a general quantum field theory description of gravity from which both this way of talking and the semi-classical version come out as approximation schemes. And I'm going to talk just briefly about the shape of that. So here at last, if you like, is my general statement of what I mean by low energy quantum gravity by the actual theory. So I'm going to assume, and I'm not sure, I know people in the audience are going to have quite varying levels of background in quantum field theory, so I'll try to get the sort of general picture here, and I can go into more details for anyone who wants them. I'm going to generally assume that the way we write down a quantum field theory in modern physics is by a path integral. So my field theory has some degrees of freedom described by something like a classical field. My quantum states can be understood as superpositions of classical field configurations. Not the only way to understand them, but it's available. And if I want to know what's the transition amplitude between some initial quantum field configuration and some final field configuration, I do so by integrating over all of the various ways of filling in the classical fields between that initial configuration and the final configuration, and I weight each integral by a factor e to the is, where s is, well, nominally is a classical action, but is really just some functional of the fields. That's the general form of quantum field theory in modern high-energy physics. And then once I've got the transition amplitudes, I've got the dynamics of the theory, and I can extract the other Hilbert space things. So pause briefly. Let me touch base unit. Do you want me to catch up your time, or can I have the?
I was already factoring in that we started late.
Yeah.
So
Yeah, that sounds fine. I'm probably going to talk for about another 10 or 15 minutes, and then a couple of the later bits of this, I think perhaps I'll leave to come up in the discussion, so we've got more time You know, if people want to talk in those directions, they can. If they want to focus on other things, they can. Does that work?
That sounds great.
Great.
Yeah.
Okay, terrific. So, if I want to do general relativity as a quantum field theory, all I need to do is use the same general recipe. So my fields are G and some matter placeholder phi, which could be nothing if I'm doing quantum vacuum general relativity. It could be a Klein-Gordon field. It could be the full collection of fields in the standard model if you're feeling masochistic. In any case, they're quantum mechanical fields described in the usual way quantum fields are described. And then I have an action, which is a sum of a gravitational action just for G, the Einstein-Hilbert action, or at least the leading order, the Einstein-Hilbert action, plus the usual matter Lagrangian, so the standard model Lagrangian or the Klein-Gordon Lagrangian or whatever you like. That's my general formal statement of the theory. Now notice it hasn't been stated on the assumption of a classical of some background, hasn't been stated in terms of particles or fluctuations. It's just a path integral. But we don't know how to evaluate path integrals. A dirty little secret of physics is we hardly know how to evaluate anything, exactly. One of the most influential things I was told as a physics undergraduate was there's only about 5 problems we know how to solve. You know, the old joke about physicists imagining a spherical cow very much gets at this. The remarkable thing about physics is you start by assuming your cow is spherical and then model its deviations from sphericality via perturbation theory. Works really, really well. The only path integral we know how to do is the infinite dimensional version of e to the minus x squared over a squared. But we can approximate an extraordinarily large range of path integrals as expansions around that object. And the general framework of doing that, or at least a general framework of doing that, which I find at least very helpful in thinking about quantum gravity, is what gets called the background field method. And I want to just quickly say what that is in general QFT and then quickly say how it works in gravity. So in general QFT, I do something like this. I start with my path integral. Then I just do a change of variables. So I say I'm integrating over the field phi. I will rewrite the field phi as phi naught plus chi, where phi naught is a fixed variable. Remember, the path integral is just an integral. So a change of variables like that has no physical content. It's no more physical than the fact that if I'm integrating dx, I can say y equals x plus 6 and integrate dy, and dx equals dy, and I can now do my integral using the dy variable rather than the x variable. So I'm doing a change of variables where I'll re-express my integral in terms of a new variable that's the old field minus some fixed field. And if I do that, I can rewrite the action, the action of the whole, the full action is equal to the action of the fixed field plus the difference between the action of the fixed field and the whole action. That's boring and trivial. And I can rewrite the path integral in those terms. And in doing so, I'm re-describing the quantum field theory as a new quantum field theory of fluctuations around my arbitrarily chosen fixed field. But again, I want to stress there's no physical assumption being made there. There's no hypothesis about the world being made there. It's just a change of variables. It's just math. However, if I want that quantum field theory to be stable and to be analyzable by the normal methods of quantum field theory, it had better be that the expected value of the fluctuation field with respect to some quantum state that's appropriately called a ground state for that setup is 0. Without that, I'm going to have sort of runaway fluctuations in the theory. So if I want to say I want to use this and re-describe this setup as fluctuations around a field, it needs to be a stable setup. And that requires a condition on the expectation value of the fluctuation. And that gives me a self-consistency problem of exactly the sort we're used to from other bits of physics. Because I'm now saying, choose my background, evaluate the fluctuation expectation value with respect to that background, and now solve for the requirement that I get 0. If I adjust the background fluctuation split, I'll adjust the expectation value of the fluctuation. As I adjust right, I get 0. And then I've got a situation that I can describe by ordinary QFT methods for fluctuations normally described in terms of particles around that background. And specifically, if you ask what equation does that lead to, it leads to a semi-classical equation for the theory. It leads to an equation in the form I have here, where the variational derivative of the background action with respect to the background field plus the expected value of the variational derivative of the extra term, the quantum term in the action, is 0 when evaluated on my vacuum state. And modulo a whole bunch of technical details, you can use this to determine the background field value. The classic application of this is in spontaneous symmetry breaking. If you know anything about the Higgs mechanism, where the vacuum has a non-zero expectation value, in elementary discussions you often see that discussed sort of semi-classically. I'll start by solving the classical theory, working out the classical action 0, and then I'll quantize around that. But that's not really satisfactory because that involves a quantum classical split of a rather unprincipled kind. The background field method is the general method we use in quantum field theory to study spontaneous symmetry breaking in a way that keeps the whole thing quantum mechanical. And this allows us, for instance, to consider quantum back reactions that change the 0 of the symmetry breaking, or in some cases even generate symmetry breaking and there was no classical symmetry breaking at all. We can do that in gravity. If we apply the same technology in low energy quantum gravity, then the semi-classical equation will determine the ground state of an effective quantum field theory. And it'll do it dynamically. It won't be that I've stipulated in advance that this is my classical field and now I'll quantize fluctuations around it. I start with a full quantum theory specified by a path integral with no background at all, and then I look for solutions to that theory in certain approximations. And which approximation is going to be relevant to a given situation is going to depend on contingent features of that situation, just as we find in other applications of approximation methods in physics. So I'm getting out the background split dynamically as part of finding the solutions to the general relativity quantum field theory. I'm not imposing it as part of the very definition. And that gives me a situation where in the vacuum state, or the ground state of that theory, I've got semi-classical gravity, and then I can describe excitations around that in the language of quantum field theory in terms of matter excitations, in terms of gravitons. So I want to claim that theory, and I don't claim this is like some brilliant observation. This is pedagogy, and I think this is at least tacitly understood and often explicitly understood in lots of the physics literature. I want to claim that this theory is a satisfactory quantum field theoretic description of general relativity in a background independent way at the level of the formulation of the theory at low energies. It needs to be cut off to be well defined, as quantum field theories tend to need, but at low energies it works fine. Okay, I'm going to pause for a moment here. Yeah, Mike.
Should I be at all, so the described matter excitations under gravity. So the semi-classical equation, as you were setting it up earlier, is functional g on one side, over g and phi on the other. And the technology, as you said, that you were just describing is accounting for just g, and I can understand phi and g to be tightly linked to each other, but in what sense do we get that excited states of this GRQFT describing matter excitation?
Good. Okay. So so if you take this as the kind of grounding of your semi-classical gravity, then the semi-classical description we just extracted from astrophysics practice is incomplete. It shouldn't be understood as a coupling of G to the expected stress energy tensor of the matter field. It should be understood as a coupling, as a coupling of G to the expected stress energy of the matter field plus the gravitons. The expected stress energy tensor of gravitons is negligibly low in applications of astrophysical significance, so we don't see that mattering observationally. But as a matter of theory, it ought to be there. The gravitons are present as fluctuations and as sources of self-gravitation just as much as the matter fluctuations are. Okay, so there's a bunch of other things I could talk about here. We can look at the limitations of this theory and where it potentially breaks down. We can look at how solid we think the evidential base for this theory is. And we can look at the relation between this theory and what you might call full quantum gravity. Actually, I'm going to say something about that last one because I think it'll be a good setup for some of the rest of the talk. Yeah. The other thing one could talk about in this framework is the cosmological constant problem. So I'm going to leave all of those, most of those things as things that we can talk about in different directions if people want to in the discussion. But I'll just mention as a coder, I said at the beginning that either we can understand quantum gravity in this sense as just quantum gravity is a theory that combines quantum and gravity, in which case it's wrong that empirical evidence for the theory is incredibly minimal. Or we can say, well, people clearly have something sensible in mind when they say empirical evidence for the theory is incredibly minimal. But in that case, the theory they have in mind can't be quantum gravity understood that way. It needs to be quantum gravity understood in a much narrower way. And I think a lot of the physics literature is best read as, in the following way. When they say quantum gravity, they mean something like ultraviolet complete quantum gravity. They mean the theory which is a high-energy completion of low-energy quantum gravity. So if, again, I'm sort of assuming some background issues in quantum field theory, and if people want to ask more about that in discussion, we can. But the normal way we think about quantum field theories, or at least most quantum field theories, is they have a high energy point to which they fail, which new physics takes over. In low energy quantum gravity, the new physics is something that's going to kick in at Planckian scales. We don't know what it is. String theory, for instance, is a candidate for what it would be. Something like a loop quantum gravity theory is a candidate for what it would be. That theory would be an ultraviolet completion of low energy quantum gravity. And often I think that's what people have in mind when they talk about quantum gravity. And that thing is genuinely very unresponsive to feasible experiments. That thing genuinely is directly probable only at Planckian energies or in comparably exotic regimes. What could that thing be? It can't really be a field theory in the normal sense of a field theory. There are loopholes and caveats here, but there's at least a fairly straightforward reason to think it shouldn't be a field theory because our field theory methods are breaking down at these kind of scales. It's one nice little thought experiment is to think, okay, suppose I tried to use field theoretic methods to push beyond the Planck scale. Well, in field theory, we classically analyze energy scales in terms of particle energies, and I say doing field theory at a high energy involves having higher energy particles. If I do field theory and I make energies larger and larger, particles get smaller and smaller. The effective size of a quantum mechanics particle in QFT is its constant wavelength. Constant wavelength scales as 1 over the mass of the particle, so the mass of the particle gets smaller and smaller, so the size of the particle gets smaller and smaller as it gets heavier. In general relativity, no particle could be confined inside its own Schwarzschild radius, because then it would be a black hole, not a particle. And in general relativity, therefore, the minimum size of a particle gets larger and larger as the mass of the particle goes up. Schwarzschild radius is proportional to mass. Those lines cross at the Planck scale. So if you try doing collisional experiments higher than the Planck scale, you just get black holes. You get a Planck mass black hole or larger than Planck mass black hole. The normal way we do experiments and describe phenomena in QFT is broadly, if I hit things together harder, then more energetic things fly out. The more energetic the particles I collide together, the more energy I get back out. But black holes decay by Hawking radiation. The frequency of Hawking radiation decreases with the mass of the particle. So if I collide particles together at energies higher than the Planck scale, I get out decay products that are less energetic than the Planck scale, and that just increases as I increase the energy of the particles. So we've got quite good reason to think that whatever the theory is that's applicable, that ultraviolet completes low-energy quantum gravity. It's not just more quantum field theory. It's not more business as usual. It's something new. And it's something which, it might not be the final theory, but it's not a theory with a length scale constraint, because the very notion of a length scale constraint is breaking down at these sort of points. And I think you can also see, if you understand quantum gravity like this, why, at least in the sort of high-energy physics tradition, people don't really very cleanly separate the search for quantum gravity from the search for a unified theory. You know, the reason why an ultraviolet completion of low-energy quantum gravity also has to be a unified theory isn't because of some aesthetic desire for unification. It's because your theory needs to handle things like the scattering of protons or the scattering of quarks or gravitons. Yeah. At lab energies, the scattering of quarks or gravitons is not a particularly significant phenomena, but at Planck scales, then the quark-graviton cross-section is large. So if your theory wants to be empirically adequate, it's going to have to be a theory of all of the relevant fields. So anyway, the sort of take-home of there is that a lot of the time, people use quantum gravity, I think, effectively, tacitly, to mean something like the ultraviolet completion of something like this theory I've been discussing. And in fact, a lot of the time in many corners of quantum gravity research, our surrogate for direct evidence of that theory is the ability to reproduce certain things you can calculate inside the semi-classical theory, or more generally inside the low-energy theory, from the high-energy theory. In other words, we feel moderately confident in trusting the low-energy theory. It contacts experiment in lots of places, and so we try to reproduce the low-energy theory using our high-energy theories. Okay, I think at that point I'd like to stop rather than come to some grand conclusion. There's a bunch of places we could go if people want to, but there might well be other places people want to go that aren't anything I've thought of so far. So let me kind of pause there and throw it open if that works. I'm just going to get some more water while
Yes, good. I'm just going to... that didn't do what I expected. Just give me once. I'm just going to change the recording here. Oh, that is what I want. Did they really delete QuickTime? Oh, there. No, you're okay. I just wanted to record off this mic. Oh, well. They seem to have deleted most of the apps, so, but I think this should do it. Let me just... do you want to just take questions for a second, and then I'll... just give me 1 minute. This will be all right.
Okay. Let's start with the discussion and questions and answers.
Yes, so David, I like this idea of recognizing that we have a functioning quantum gravity theory, but I also think the last point you make, that what the physics community is often after is a UV complete theory. But I wonder then if your proposal or the recognition of semi-classical gravity as a theory of quantum gravity comes with any kind of consequences for the context of discovery, say that we should really approach these issues in a different way, or is it still useful that, like in a sense we could say what we are attempting to do in high energy physics is a very ambitious project, that we want not only a theory of quantum gravity but also a UV complete one. Is there could it be sensible to sort of drop that requirement of UV completion for purposes of perhaps finding more different kinds of theories, and therefore perhaps further along the way have more options on the table for what might be UV complete theories? So is there such a proposal for how this might help the context of discovery?
Good. Okay. I mean, let me just do a quick qualifier first. I don't want to say that semi-classical gravity is a low-energy quantum theory of gravity. I think semi-classical gravity is a useful approximation scheme for a low-energy theory of quantum gravity. But that's just a quibble. Beyond that, well, look, in a certain sense, by all means, let's look for low energy quantum theories of gravity that aren't QFT, that aren't effectively a QFT version of general relativity. But we go back a bit to the fact that theory has a lot of evidence behind it. If that theory doesn't have semi-classical gravity as an appropriate approximation scheme in really a very wide range of places, it's just going to be in conflict with observational data. The empirical constraints for fluctuation phenomena coming out of inflation are less tight than that, but they're not zero either. And then you just have the sort of theoretical grounds that quantum field theory as a way of doing things is so effective, and in more ways than one, and that our discussion of matter fields is quantum field theoretical. It's not, maybe it's lack of imagination, but it's difficult to see easy ways of having a fully quantum mechanical theory of gravity that couples to a quantum field theory of matter that doesn't look a lot like a low energy quantum gravity in my sense, particularly given the evidential constraints. So by all means look for those alternatives. I mean, by all means look for alternatives to anything, but it's a quite constrained space, I think. I mean, in terms of the sort of context of discovery for high energy physics, I think it's useful in thinking what are the success criteria for a quantum theory of gravity in that sense. And I think this is useful to think about, again, as philosophers. It's useful to think about if you compare the way string theory gets done with the way some other styles of quantum gravity get done. I guess I'm thinking something like the causal set theory would be an example. What need one to have done in order to have got a quantum theory of gravity that's satisfactory, never mind true? And one way you might think about it is that a satisfactory quantum theory of gravity is one which does indeed reduce to classical general relativity in an appropriate regime, and does indeed reduce to quantum field theory or flat space-time in another appropriate regime. If you'd asked me like 6 or 7 years ago what a quantum theory of gravity had to do, I'd have said something like that. And I think one way in which we understand the context of discovery here better is if we think that doesn't really capture what a quantum theory of gravity's got to do, because actually we don't have these separate magisteria of classical general relativity phenomena and flat space-time quantum mechanics phenomena. We have a very large overlap region there. That needs to be recovered too. It doesn't necessarily follow that we have to recover full low-energy quantum gravity, because again, there are regimes of that theory that are only shakily tested. But we have to recover at least the highly tested regimes of it. And you can certainly see why the physics community, or at least the high-energy physics community, the string theory community, has sort of taken as a starting point that it wants to recover the whole of low-energy quantum gravity. I don't know if that speaks to some of...
Yes, but in a sense it then, you could say, vindicates, for instance, string theory, because it precisely is able to get that theory that we say is reasonably empirically tested, and therefore, insofar as string theory can reproduce it, that seems to at least provide some, I would suggest the pursuit-worthiness of, for instance, string theory.
Yes, I think so. I mean, sociologically, yes, that's definitely what string theorists think. Normatively, I think they have a point. But more broadly, I think it's often not, partly, of course, string theories have the lion's share of physics attention. It's often relatively easy in the string theory literature to see the ways in which string theory tries to deliver on these things, and also to understand the limitations and problems of that program. It's actually quite hard, if you read a lot of the often much smaller literatures on other approaches to quantum gravity, to even quite see what the recovery has been, or what the framework of getting at it is. And I think partly that's because, just sociologically, people in string theory are very comfortable with modern quantum field theory, and so think about recovering GR as a quantum field theory as a very natural way to go. As if your approach is starting with something like classical general relativity and trying to have something that counts as a quantum version of it, you're likely to look in slightly different directions. Also many of these things move very fast. I honestly don't know, for instance, I'd love to know this better, how well we're currently doing in the loop approach to quantum gravity in recovering kind of low energy regimes, recovering Minkowski space-time, recovering fluctuations around Minkowski space-time. There was a point where that was seen as a very major problem in the field. I know there have been some advances in it. But from the methodological point of view, I'm suggesting that would be one of the ways in which one would want to assess what progress had been made in thinking about loop space quantum gravity as an approach to quantum gravity.
Okay, yeah. Emily?
So just about sort of the social controversy is largely about the social movie completion. Why do you think physicists are so much more worried about the absence of movie completion for gravity than for the movie completion for all the other interactions? Is that just sociological, or is there a reason for that?
I don't think they separate the questions out very much. I mean, the UV completion, the thing I've called low energy quantum gravity has the standard model as its matter component. So a UV completion of that theory, UV completes the standard model as well. But I think, in some ways I want to push back a little bit against the claim that people are not worried about that for other theories. I mean, in a certain sense, you can think about the Higgs boson as the UV completion of electroweak theory. If you think about electroweak theory empirically, in the absence of the actual mechanism of electroweak symmetry breaking, it's a non-renormalizable field theory which breaks down around the Higgs energy. And so some new physics had to turn up to fill that in. In some sense, it's unutterably disappointing that new physics just seems to turn out to be an implausibly finely tuned scalar boson, but nonetheless, it's kind of doing that thing. But again, you sort of can't really. I mean, of course, you could do the intellectual exercise of looking for a UV completion of vacuum general relativity, but that won't be empirically adequate. So if you're looking for an empirically adequate UV completion of quantum gravity, it's automatically a UV completion of the whole interacting field theory set.
So, you go ahead, please.
So there's this linguistic emphasis on gravity as being a thing. Would you say that's just kind of perhaps placing more emphasis on that than is justified by the actual problem?
I think probably, but I also I'm not sure that the linguistic evidence is actually present in the mainstream communities that does most of this. I mean, string theory talks more about gravity than it used to, largely because of ADS-CFT correspondence and a big focus on black holes in the last couple of decades. But traditionally, string theory didn't tend to get described by its practitioners as predominantly a quantum theory of gravity. It was a quantum theory of gravity, but it wasn't the thing that they predominantly emphasized. The thing that was emphasized was more that it was a unification of fundamental forces. And its description in philosophy or as a quantum gravity program is not wrong, or even it's not even a distortion, but it's certainly a focus that's slightly different from the focus that string theorists themselves have tended to have.
So a couple of comments. I have a queue going if people have questions. If you have a follow-up question, I guess I will do the usual thing if you put a finger up. So was that a new question, Mary, or did you want to come in on this? Third thing, I didn't mean to put this up, but you can see whether you're speaking loudly enough to be recorded. So please.
Yeah, is there a point that we discussed about perturbations?
Mm.
So there is actually a doctrine problem with electric physics where you quantize in general when you perturb, or first you perturb and then you quantize. And this operator did not commit
Mm.
So that has created some problems with different kind of electric field models.
Sure.
So this is a comment because at some point you put the perturbations.
Yeah, and methodologically, I would normally want to be this is part of my point. I think methodologically, a satisfactory framework had better be quantizing. Well, I'll say this now. I'll qualify it. A sensible framework would be quantizing and then permuting, because I want my quantum theory to be a full quantum theory in which perturbation is an approximation regime. But also, I want to resist a little bit the idea that quantization is a good way to talk about QFTs. I mean, I think the sense in which the action is a classical action is very formal. I mean, it's really just the way I write down a quantum field theory directly is just to write down an action function and a path integral. But that's not in any way in conflict with what you just said. So anyway, thank you.
So yeah, Bruno was next.
Yeah, you did mention that the distinction between the classification between semi-classicals and phenomenological can be blurred.
or you have description at the level of multi-particles, you have a constant level of particles, and then the field theory that if you try to define this state for which you have an undiscrete number of particles, that needs complications as well. All I'm trying to ask is how much evidence there is for this particular coupling versus any other possible coupling between quantum maximum and classical gravity.
So what you're doing normally, you're calculating. You've got your, normally speaking for these cases, the variation in the metric is on scales very large compared to the typical quantum mechanical interaction scales. So normally you're going to study your quantum fluid. You're going to work out the equation state for the quantum fluid on the idealization. You can just put in an inertial frame. Then that's going to give you a calculation of the stress energy tensor. That stress energy tensor is then, the expectation value of that stress energy tensor is then going to be plugged into the G equals T. So in that sense, if by the particular coupling we mean the G equals T coupling, I don't think that's very strongly evidence. But it's certainly true that there's the solution approach has a division of labour going on. I'm going to work out an equation of state, and then largely it's the equation of state I plug into the field equations. And that's not unusual. I mean, that's not. I think it's true. I think in most of the more established machinery that I'm not. I don't have gravitational variation so violent that I need a kind of dynamical theory of how that mixing is happening. I'd wonder about supernovae here, but in most cases.
Yeah, just I tend to think it much more phenomenological than classical in that sense, because quantum modeling tends to be confined to very particular inputs.
Yeah, I want to push back a little against that. I mean, if I think about, so take white dwarfs and neutron stars as an example. I mean, our modelling of these things is very microphysical. I mean, white dwarfs electrons are weakly interacting. White dwarfs are very well understood. We have a micro-level quantum story about their equation of state. Neutron stars are harder because neutrons interact strongly, but we're still doing a kind of bottom-up QFT. I mean, not historically, but in kind of modern ways of trying to study neutron star structure, we're still doing a kind of bottom-up QFT quantum field theory StatMech management of the neutron fluid.
Yeah, for the neutron star, I think it's very hard from that. But for white dwarfs, I wouldn't describe it exactly as field theory, but more like quantum mechanics of.
Yeah, no, it's not it's not a QFT problem. Yeah, you're right. It's many. Yeah, the white dwarf is many particle quantum mechanics. Agree with you. Yes, so there's a distinct there's a fine graining of the distinctions I was drawing. I was looking at like how much gravity you need to put in, but you can also ask which pieces of quantum mechanics do we use. So there are going to be regimes that are, among the quantum gravity regimes, I can ask, do I have non-relativistic gravity or fully relativistic gravity? Also, do I just have non-relativistic quantum mechanics or full quantum field theory? So neutron stars are going to be a full quantum field theory, but probably only small perturbations away from Newtonian gravity. Supernovae are going to require both relativistic gravity and relativistic field theory. White dwarfs are going to require only Newtonian gravity and non-relativistic quantum mechanics.
Okay, good. Guy, you're next. And can I ask people to make sure they project so everybody can sort of hear the questions as well? Yeah.
So, if I understand your point correctly, what's in B, the conclusion would be that to explain this in B somehow we have to linearize quantum gravity theory. Because if we match calculations and they quantize everything, and then that could be our main evidence that somehow we need to use linearized quantum gravity to explain this one phenomenon. That I get clarified.
Pretty much. I mean, perhaps I replace we have to do it with it's in fact what we do.
Okay.
I don't think I haven't really made a case of there's no other possible modelling method, just that's how we model it.
Yeah, because it seems to me that, okay, so first of all you have to believe in inflation, and that's what we do, I guess. But it's it's hard to infer out of this explanation that indeed we're using absolute gravity because we can always clean away this element of the metric if we want. That's why I think people are really excited about detecting tensor modes as in CMB because then they figure tensor modes, the metric fluctuations will be gauge invariant. So if inflation was true, that would be a direct proof of linear aspect gravity. While I guess if you focus only on scalar simulations, I think it's more contentious because of the gauge choice.
Yeah, I mean, I have some sympathy with that, and I should say also, I think you know the physics of this significantly better than I do. So the minimal claim is just, well, I suppose a combination of two things. Firstly, semi-classical quantum gravity is not going to be able to handle it just because it's not sensitive to fluctuations. By construction, it's not sensitive to fluctuations. So whatever technology we need to use to handle these things is going to have to be something that goes beyond semi-classical gravity. And if we have a story, if we have an origin story for fluctuations that's where they're quantum fluctuations, then I'm going to need a quantum theory of gravity that's not semi-classical gravity. And then further, if you just look at what people actually have been using, they're often using this kind of thing. But that's certainly a far cry from saying that forces a confirmation of that particular theory. And that kind of speaks to my earlier comment that I don't know and would love to see a really careful analysis of, you know, what are the moving parts in the passage from the sort of micro quantum mechanical description of the fluctuations and their coupling to gravity through to the phenomenology. I mean, obviously that's a very indirect pipeline, and I mean an example would be I'd love to see a clear understanding of what room for manoeuvre have we got in how we think about quantum gravity in understanding just the existing fluctuation structure, and to what extent would that be closed if we get indirect evidence of graviton scattering. I'll freely say I don't feel in control myself of the physics of the cosmology part of this to the degree that even to the degree that I feel I do in the high energy of black hole sectors. I think there's lots of interesting low hanging fruit here on the physics philosophy borderline. Well, I'm not intending to say anything especially controversial. There is a mainstream line in.
It's not quantum gravity. Everything, the quantum becomes stronger or the quantize the perturbation, but there's not quantum gravity.
Well, if I look at just elementarily, if I look at, actually, sorry, I'm responding, but I'm getting. You had a line in order, so I don't know.
No, that's
fine.
fine.
Okay, good. If I just look at an elementary derivation of this, I'll normally do something like say, okay, I've got my quantum field, I've got my quantum matter field, and my metric, and I'll treat the metric as a quantized fluctuation. It's slave to the matter field, so it's not. I don't have gravitational degrees of freedom, but I do have superpositions of different metric fluctuations because I have superpositions of different matter states, and the metric is slave to them. Again, I'm not trying to say anything terribly contentious here. I'm just doing Weinberg exegesis.
Yes, please.
Maybe just to come back to this distinction between classical general relativity quantum applications of it.
Sure.
I'm just wondering, like, what would even be a classical application of general relativity beyond maximum general relativity if we have all matter being quantum? I mean, I sympathize with the point of, as always, kind of combining quantum theory when looking at matter, but saying I do gravitational lensing, then I don't really need the quantum theory. You know, the stars that do the gravitational lensing, they are ultimately quantum. But I would also be reluctant to say that this is involved.
Yeah, I agree. I put most gravitational lensing in very much on the phenomenological gravity side. We don't really care how the stress energy tensor is formed. We just want to image it through the lensing process. Just for the sake of a concrete example, here's a hypothetical experiment that would definitely count as a test of the classical GR regime for me. take a humongous laser. I know the actual machinery of the laser is quantum, but I'm going to ignore where the laser beam came from. I've just got my laser. I've got a coherent phase of the electromagnetic field. It's zooming through space, and it's incredibly energetically dense. So energetically dense that I can measure the deviation of test particles around it. So I can't approximate the metric around the laser as a vacuum metric. I really need to say the actual, I calculate the classical Faraday tensor. I plug its classical stress energy tensor into the Einstein field equations. I calculate what the metric is, and then I test that by looking at the bending of light around the laser beam or something. That would theoretically count as a genuine experimental regime that classical general relativity describes. And then the claim is, well, the actual application range of GR doesn't include things like that.
So you'd want to be able to derive stress energy tensor because most astrophysical objects are too complicated.
Well, it's not so much just they're too complicated, it's that the derivations are quantum. I mean, if I want to know the stress energy tensor of this table, I can obviously just empirically measure it and ignore where it comes from. That's phenomenology. If I want a microphysical understanding of what the stress energy tensor of the table is, I'm going to need to the physics of the table at the micro level, and then I'm going to need some quantum complexity. I mean, you could debate whether that's true for the table. I suppose you could just extract away the thing that binds it. But if I've got something that's gravitationally bound, so I can't just do that, then I'm going to need a quantum description of it. So we don't have this just in classical mechanics is false, and this further in solid matter needs quantum mechanics to understand it. So it's not surprising that we don't, by and large, have classical microphysical accounts of stress energy tensors. I mean, in a sense, that should be saying something that's perfectly obvious, but you do. There's a sufficiently large focus on classical general relativity in the sense I describe it, in the kind of interpretive literature and philosophy of space-time, philosophy of GR, that I thought it was worth sort of pulling it out to make the point that that's not the regime of GR that's empirically relevant.
I'm going to abuse my privilege and ask one question, although we only have about 2 minutes, so maybe. I think at the beginning of the talk you talked about empirical predictions, but by the end you were talking about evidence, and maybe even confirmation at some point. So what I'm kind of thinking is, I think it's true that most people in the community, vast majority of people in the community, really do think that sort of EFT general relativity will be sort of empirically applicable in its regime for sort of pre-empirical kind of reasons because of its sort of success. So how much do you want to push that this is really sort of evidential, confirming these theories in a strong sense rather than something kind of weaker there?
Yeah, so I'm not making any very sophisticated distinctions here, and if I'm varying between these, it's mostly stylistic. I think there probably are more interestingly fine-grained distinctions than I'm making that could be brought out here. But I suppose I want to say semi-classical GR in the regime in which we'd expect it to work, I think is very solidly evidenced, arguably confirmed by a plethora of data. You'd want to say some much shakier things about the non-semi-classical regimes, but you wouldn't have nothing to say or something to say. And I think it's, again, I spell this out a lot in the written version of the paper, but it's worth saying, of course, any test of a theory as complicated as a quantum field theory is always going to be a test of a certain approximation scheme of that theory in a certain regime. So the sense in which we have evidence for quantum electrodynamics is we have tons of incredibly precise evidence for the theory in tons of different regimes. For low-energy quantum gravity, we have variable amounts of evidence for the theory in various different regimes. So at one extreme, I think the evidence for the semi-classical sector of the theory is really good. At the other extreme, low-energy quantum gravity predicts that you can do the two-slit experiment with gravitons. it should be that I can generate an incredibly attenuated beam of gravitons, and I can detect one. I should be able to find that I can detect one graviton at a time, and they're quantized. And yet, if I send the gravitons past a mass lens or something that diffracts the graviton beam, I should expect the full diffraction pattern, and not, even as I turn the beam down to one graviton at a time. We are, to put it mildly, not close to being able to detect individual gravitons. So that's an area where we have clear and abundant evidence for QED's predictions, and with no realistic near-term prospect of evidence for low energy quantum gravity predictions. But
I think the point I was thinking, a lot of these tests aren't, I would say, weren't particularly severe tests of semi-classical gravity. I mean, the thing that's more up for grabs is whether we're modeling the supernova rate, we have the equation of state rate for this thing, the quantum mechanics of it. That if things went wrong, it seems, I think many physicists would think that's, we were more likely to be wrong about that.
I guess it depends
semi-classical gravity.
I guess it depends what severe means. If I start with semi-classical gravity, and then I specialise to the sector where matter is non-relativistic and gravitation is Newtonian, I'm going to derive a quite specific theory, which I can then apply to white dwarfs and get some pretty specific predictions about, for instance, the Chandrasekhar limit. And those are the Chandrasekhar limit is very strongly supported empirically, and is quite sharply calculable inside that framework. So I'd regard that as really very good evidence that that framework is correct. Now, of course, it's only a particular regime of full quantum gravity, and it doesn't in any way logically require that there isn't some different relativistic generalization that still gets that regime out. But again, I think it's not so much that it's not particularly severe, it's that it's only in that particular sector.
Right. Okay, good, great. Well, I think we're out of time. But just before I say that, coffee, I think, is ready upstairs by the reception. And we will start, because we started a little late, so let's take a 20-minute break and reconvene here at 11:05 for Chris's talk. So, thanks again, David.